So 153 is the regular payback. 168 is the discounted payback. So assuming cutoffs are long enough, based on regular payback, which one of these we would pick? One, which pays back in 1.86 years. Two, in 1.53 years. What do you think? Yes, two is the correct answer. Because when comparing payback periods, we want low numbers. The quicker we get paid back. But does that necessarily mean that's the right decision? We'll see. This project costs $715, but project one costs 1.8. Yes, I am getting my money back faster in the smaller project, but that does not necessarily mean that it's a good thing. In fact, looking at the NPV, I get 610,000 in NPV on project one, but only 488 in project two. So in that sense, it is better. Same idea with PI. PI would have picked project two as well. Similarly, IRR would have picked project two as well. But none of those criteria, payback period, PI, IRR, they don't know anything about the scale of the problem, but NPV does. So if there's a conflict, we always go with NPV. In fact, we already talked about this. We could have also done incremental. In fact, let's go ahead and do it. This is 1 minus 2. Since 1 is a bigger project, that's 715, 915 is the cost. That's 700. That's 73, 173, 213. It's 474. Of course, you don't have to be pedestrian like this. You could calculate them using Excel functions, but this is the IRR of the incremental cash flows. It's pretty high. So actually, based on incremental cash flows, you should pick project one, because we wrote them as 1 minus 2. And which obviously also agrees with the decision based on NPV. In fact, the incremental NPV is exactly equal to the difference between the NPV of two projects. You want me to do more problems on this, or you want me to go over maybe cash flow kind of stuff on chapter 6? Let's do some problems. Okay. Let's start with some basic stuff. This is a restaurant. They're considering the purchase of a souffle maker that costs $8,600. It has an economic life of 5 years and fully depreciated by the straight line method. The machine will produce 1,100 soufflés per year, each costing $2.15 to make and priced at $5.95. We know the discount rates and tax rate. It does not say anything about any potential, what you want to call, any potential I lost my chain of thought. The potential salvage. Let me get the. Remember, we have a template for salvage and depreciation. I mean, in this case, it just happens to be relatively simple because we're going to need the depreciation numbers. The machine costs $8,600. Salvage value is 0. Tax rate is 21%. Tax life and project life are the same. And it is not makers, it's straight line. Okay. This automatically calculates us the depreciation for each year, which we're going to need. Now let's talk about sales and costs. Let me use a new sheet. Unit sales. Unit price. Unit variable cost. So each year we're going to sell 1,100 of them. Selling it at $5.95. But it costs us $2.15. Of course, these are dollar numbers. You know, I'm a little bit anal about formatting. So if I do years, 1, 2, 3, 4, 5, sales, 1,100 times $5.95. Let me fix them. Variable cost, 1,100 times $2.15. Make these calculations a lot easier, but I just want to show you the individual steps. Depreciation. We already calculated them here, so we'll just use them. I mean, in this example, they all happen to be the same. We can calculate net income. We can also put tax rate here. sales minus variable costs. In this specific example, we don't have any annual fixed cost minus depreciation times 1 minus tax rate. Okay. Of course, what we're going to need is operating cash flow. Which is equal to net income plus depreciation. Now, in terms of, there is no change in net working capital. In fact, let me introduce insert. These are all zeros, but net capital spending. Machine cost. We have it here, but I'm gonna enter it anyway. Since there is no salvage, net capital spending is zero for all of the years. So CFFA is operating cash flow minus net capital spending minus change in net working capital.